In this video, I will be explaining linear and nonlinear regressions, but more specifically, I will be applying both kinds of regressions to a widely used model known as the Antoine equation. To further elaborate, the Antoine equation is a semi-empirical model that showcases the relationship between vapor pressure and temperature for pure substances. We want to use this model to be able to fit the vapor pressure as a function of temperature, where we have three unknown coefficients, A, B, and C, thus the Antoine equation. Log base 10 of the pressure equals A minus B divided by C plus the temperature. Now, experimental data is needed in order to find A, B, and C because they will vary depending on which substance you choose. So for this video, I will be using experimental data that shows values for the vapor pressure in pascals and the temperature in kelvins for water. So let's open up this data. Now, once we have the data open, we're going to want to turn this into a raw CSV file, copy the link, and open up Collaboratory. Collaboratory is a free Jupyter/notebook that is available for anybody to use. Now that we have this open, I'm going to be using a links command shell called wget, followed by the link to download the data into Collaboratory. And we can make sure that it's been downloaded by going into the file manager and verifying that it is in there, and it is the water vapor pressure.csv file. So if we double click it and open it, you'll be able to see that these are comma separated values, with the first column being the temperature in kelvins and the second column being the vapor pressure in pascals. So now I'm going to be using a function within, before I can do that, I'm going to import numerical Python as NumPy as NP. And then I'm going to be loading the data with another function, with a function within NumPy called loadText. I'll input the name of the file, and since it is comma separated values, I will be assigning a delimiter of commas. From here, we're going to want to create our variables for the temperature and the vapor pressure values. So for temperature, I will simply use T, and we're going to assign all of the rows in the first column to the variable T. And for the pressure values, since we have to take the log of the pressure values in the Antoine equation, I'll call the variable log P. And we actually have to take the log of these values. And then I will assign all of the rows in the second column to the log P variable. And remember, in Python, the index starts at 0, so the first column will be 0 and the second column will be 1. At this point, we're going to want to plot our data. And to do that, I will be using a very nice plotting program called Plotly that allows us to create subplots. Next, I will be importing plotly.io, which is Plotly input output, as PO. And I personally think that the white background on the subplots is kind of bright, so I will make the background dark. So from this point, we actually can start coding the plot itself. I will do fig equals make subplots and set the rows and the columns to 1 since there's only one for each. And since we have this kind of data, we are going to want to make this into a scatter plot. So I'll do fig.addScatter. We will set the axes to their respective values, where the x-axis is the temperature, so we'll set it to T, and the y-axis will be the pressure value, so we'll set it to our variable log P. Our mode will be markers, and the name will simply be data since it's our experimental data. We can close this, and just to verify that we have the data loaded, I will insert another line and simply type data. And there it is. So we are safe to close out the file. I personally think that this is a little too big for my liking, so I'm going to do fig.updateLayout and change the height to 600 and the width to 800. And there's our data. Now we'll be able to kind of tell if this is good data or if it is fitting for the values for water, because we can use the normal boiling point of water, which is 373 Kelvin, so about here. And we can go up to where it aligns with the pressure values on the left-hand side, and we notice that it aligns with 10 to the 5 pascals roughly, and that is correct. So we know that our data is good data.
Initially, we want to fit this data as a nonlinear regression model, but we'll also want to minimize the sum squared error. So to further explain what I mean, I'll show you. We have data points that look very roughly something like this. And we have our model, the Antoine equation. So log base 10 of P is equal to A minus B divided by T plus C. And we'll want the deviations between our model and our data to be as small as possible. So let's add up the sum of our data where we use P sub I because we start at the very first value of our data and go until the very last value of our data. And then we'll want to subtract our model. So this is our data. This is our model. But if we just did this, you might be thinking how some of the deviations will be positive and some of them will be negative. A deviation right here would be negative, but a deviation right here would be positive. But we care about whether or not they're positive or negative. So we're going to square the entire equation to ensure that all of the deviations are positive and that they'll all contribute equally. This is the sum squared error, adding up the sum squared deviations from our data and our model. We'll want to minimize this sum squared error by adjusting the model parameters A, B, and C.
We need a function to minimize, which will calculate our sum squared error. So let's define our function. Define SSE, or sum squared error, which is going to take in a vector of our parameters A, B, and C, so we're going to call that vector V. Now we can unpack the vector into the individual parameters A, B, C, equal to V. And now we can return the sum squared error. The error is the difference between the vapor pressure data we have imported and our model, the Antoine equation. So let's see how far the data deviates from the model. So I'll do return mp.sum of the Antoine equation. And we have to be sure to square it. So now we're able to use a scientific Python or SciPy optimize minimize, which essentially is a pre-coded algorithm that optimizes and minimizes functions. So we'll come back up here and do from SciPy dot optimize and import minimize. Then we can return to our previous position and minimize our function SSE. And we're going to need an initial guess for A, B, and C. And since at this point we really have no clue what they could be, we're just going to guess some random numbers. So I'm going to do 13, 5, and 1. And we know that this worked because the message reads optimization terminated successfully, and it is presenting us with X values. So to view those, we could set this equal to a variable, which I'll call para for parameters. And then I will do para.x, or I will run the code first and then do para.x. And these are the fitted parameters for the nonlinear regression. So at this point, I can really delete this and put the .x at the end, because now this is enabling us to single out the optimized value for A, B, and C for the nonlinear regression and assign them to their respective variables. I'll do underscore NL after each letter for each value to indicate nonlinear regression. So at this point, we can plot the data. I'll do fig.scatter like we did earlier, where x is equal to t still, but this time around y is equal to the Antoine equation, and we are using the specific parameters and values that we got for the nonlinear regression. Mode is lines instead of markers, and the name will just be Antoine equation. Antoine nonlinear regression. And as we can see from the plot, the data and the model fit together pretty well, but there is another way that we can go about this, so let's shift gears.
Another way that we can try fitting the Antoine equation to our data is by transforming it into a linear regression rather than performing a nonlinear regression. So first we'll start with the Antoine equation, which we can recall is log base 10 of p equals a minus b divided by t plus c. So from here we can multiply both sides of the equation by the denominator term t plus c. To get t plus c times log of p. And I would like to note that from this point on, I will be omitting the base 10 from the log of p just to make the annotating a little bit easier, but it is important to remember that it is log base 10 of the pressure. So like I said, t plus c times log of p equals a times t plus c minus b. And after that, we can multiply each of the terms through the entire of the equation and get t log of p plus c log of p equals A times T plus A times C, minus B. At this point, I'm going to subtract the C log of P term from both sides. So we're left with T log of P equals A times T minus C log of P plus A times C minus B. Now, you might notice that the term AC minus B is simply some fitted parameter, so we can refer to it by just a constant, and we'll refer to it as D. At this point, we've set ourselves up to be able to perform a matrix multiplication. So I'm going to rewrite our newly derived equation, where again we have T log of P is equal to A times T minus C log of P plus AC minus B. Now at this point, we're able to set up our design matrix. And our design matrix will consist of all of our experimental temperature and vapor pressure values and simply a column of ones. So we'll have T1, T2, T3, all the way down to some temperature Tn. And we'll do the same thing for the vapor pressure values. And it is important to remember that since in the equation, the log of the vapor pressure values is negative, so we have to carry that negative into the design matrix. Negative log of P2, P3, same with the temperature values, all the way down to the negative log of some pressure Pn. And then, like I said, we'll just have a column of ones. All the way down, 1. So next, we can multiply our design matrix by the vector of our unknown coefficients, A, C, and as we refer to this, D. And actually, I will write this at the top so it doesn't get in the way. And finally, we can set this equal to a matrix consisting of this T log P term. And do the same thing as we did with the design matrix. This is lowercase p. All the way down to the temperature times the log of some pressure Pn. Now, at this point, we can't really do much because we have an unequal amount of equations and unknown coefficients. We have an n amount of equations where we have 3 unknown coefficients. So what can we do? Well, actually, we can multiply both sides of this equation by the transpose of the design matrix. Now, why can't we just take the inverse of the design matrix as it is? Well, the design matrix is not a square matrix. It's an n by 3 matrix. And while we're here, we might as well label all of our other matrices. So our design matrix is an n by 3, our vector matrix is a 3 by 1, and our T log P matrix is this is a 3 by 1 and this is a n by 1. So knowing this, we can refer to these matrices as different, we'll give them different names. So we'll call the design matrix X, our vector V, and the T log P matrix Y. So now let's rewrite this equation. XV equals Y. And like I said earlier, we should multiply each side by the transpose of the design matrix. And we'll call that X to the T. So by doing this, we have actually made the design matrix turn into a square matrix. And how do we do that? Well, the transpose of the design matrix is simply the complete opposite of the design matrix, which means instead of it being a n by 3 matrix, it is a 3 by n matrix. So multiplying these together, we now get a 3 by 3 matrix. And remember, our vector is a 3 by 1. And our y matrix is a n by 1. Which means when we multiply these together, we get a 3 by 1 matrix. So from this point, since we have achieved a square matrix, we can now take the inverse of the square matrix. So I will rewrite the equation we just had. And like I said, we are now free to take the inverse of the design matrix and multiply it by both sides. Now, you might notice something familiar, and it's that this right here has given us our identity matrix. And if you don't know, the identity matrix is simply a matrix that is composed of ones all the way down the diagonal of the matrix and zeros everywhere else. So it might look something like this. These aren't the actual dimensions. This is just a demonstration of what it looks like. So now that we have the identity matrix, all we really need to focus on is this equation over here, which is our unknown coefficient vector is set equal to the transpose of our design matrix times the design matrix and the inverse of that, times the transpose of our design matrix times our y matrix. And this equation is actually the equation that will give us our parameters for the Antoine equation.
So coming back to Colab, now we have to code our design matrix, but that's essentially just a combination of columns. So in Colab, we will do our design matrix X set equal to mp dot c underscore t negative log of p and mp dot ones underscore like t, which is our temperature values in the first column, pressure values in the second column, and when we're coding this, we will use this function to be able to give the ones in the third column the same shape as the values of the temperature in the first column. And now that that's done, we are basically done, because at this point, all we have to do is calculate our vector, which will give us the unknown coefficients. So we can do x dot t, which is the transpose of the design matrix, times the design matrix. And in Python, when doing matrix multiplication, we have to use the @ symbol. Now we can take the inverse of this. And finally, we just have to multiply it by the transpose of the design matrix one more time and multiply that by the y matrix that we had, which was just the temperature times the log of the pressure values. And these are our values for A, C, and D. And we have to remember that our initial unknown coefficients were A, B, and C, but we assigned the A times C minus B term from the rearranged equation that we got while setting up for the linear regression. And since we sent that equal to D, we have to solve for B, but since we have the values for A and C as well, we can do that. So let's set this equal to A, C, and D so we can calculate what B is. And I'm just using underscore L after each variable to indicate linear regression. And now we can see what A, B, and C are. So A, B, and C are roughly 10, 1700, and a negative 34. So if we go back up to minimizing the sum square error for the nonlinear regression, we can input the values for A, B, and C and see what we get. And I'm going to restart and run all so the plots won't overlap. So honestly, you can notice that there isn't much difference between the previous plot and this one due to how well the data and the model fit. But the one thing that you will probably notice is this area right here where the model seems to connect the data points as if there's a true gap in this area. But realistically, the Antoine equation model allows us to calculate the pressure values at any given temperature. So we are going to do one thing to fix this. So instead of just plotting the temperature values from our experimental data, we can plot some temperature values just for the sake of plotting purposes. So what we'll do is come up here and insert a line of code. No. So instead of just plotting the temperature values from our experimental data, let's plot some temperature values just for the sake of plotting purposes. So we'll come back up to the line right before our plot, and I'm going to create a variable called tplot, and we're going to be using a function within NumPy called linspace, which linearly spaces out data, where here we will be plotting 100 points from the smallest value of our temperature to the highest value of our temperatures. And now that that's done, we have to alter our current settings for the plot. And as you can see, now the plot just fits a little bit better, and you can see the curve that has been created rather than a straight line. But since we have done this for nonlinear regression, we should also plot it for linear regression. So we'll simply copy and paste this. And come down here, add a line. And this time, instead of altering the t values, we will alter the variables and make sure that they are A, B, and C for linear regression. And we will change the name to Antoine Linear Regression. We have successfully applied linear and nonlinear regression to the Antoine equation and fitted to vapor pressure data for water by utilizing fundamental engineering concepts such as matrix multiplication and the minimization of the sum square error. Thank you for watching.